You know that feeling, right? When you just want to get a really complex idea, like, instantly. Have that aha moment without wading through textbooks.
Yeah, cutting right to the chase.
Exactly, and that's what we're aiming for right here. Today, we're diving into something pretty revolutionary, actually. It's a brand new theory,
Uh-huh.
and it's aiming for the biggest prize in physics, finally unifying gravity and quantum mechanics.
Wow, okay. That is the big one. The Mount Everest, you could say, for what, nearly 100 years now?
Right. Our two best descriptions of the universe. Einstein's gravity for the big stuff, quantum mechanics for the tiny stuff. They just haven't played nicely together.
And bringing them together, that's been the ultimate quest. It's essential, really.
Think about it. Gravity, this beautiful geometric picture of space-time bending, shaping galaxies.
And general relativity.
And then quantum mechanics. This, well, frankly, bizarre world of probabilities, particles popping in and out, fields.
Totally different language. Both work incredibly well on their own turf, though.
But try to put them together, like in a black hole or right at the Big Bang. Things just break. The math goes haywire.
And it's not just math. It's about understanding reality itself at the very deepest level. Einstein famously spent his later years chasing this.
He did, and the search is obviously still on. It's crucial for understanding those extreme places in the universe, isn't it? Where gravity is super strong and quantum effects must matter.
Absolutely. You can't ignore either one in those situations. So a full picture needs both.
Okay, so our mission for this deep dive, explore a really interesting new idea. It's from physicists Mikko Partanen and Jukka Tolkki.
Okay.
Published in Reports on Progress in Physics, so this isn't some, fringe blog post. It's peer-reviewed.
Right, that's important. Serious scientific work.
We want to unpack their core idea, see what makes it different, and we'll figure out what its potential might be for finally cracking this problem. Ready to jump in?
Let's do it. So where do we start? The fundamental clash.
Yeah, let's nail that down first. What is the basic incompatibility? Why don't GR and QM just stop fit?
Okay, well, it boils down to how they describe reality, fundamentally. Einstein's general relativity, GR, paints gravity as, well, geometry.
The curving of space-time itself, like a bowling ball on a trampoline.
Exactly. Mass and energy warp space-time. And that warping tells other things how to move. And crucially, time in GR is flexible. It's woven into that dynamic space-time. It's relative.
So space-time isn't just a static background, it's an active player.
Precisely. Now, contrast that with quantum mechanics, or more specifically, quantum field theory. It describes forces in particles using quantum fields. But these fields typically exist within a fixed, predefined space-time, usually flat space-time, actually. It's the stage.
A static stage, unlike GR's dynamic one.
Right. And time in standard quantum mechanics is usually treated as absolute, like a universal clock ticking away, marking the evolution of quantum states.
Okay, I see the mismatch. One has a flexible stage, the other needs a rigid one. What happens when you try to force them together? What are the specific train wrecks?
Well, several big ones. First, mathematically, if you try to apply the standard rules of quantum field theory, the rules that work beautifully for other forces to gravity, you just get infinities popping up all over the place in your calculations. It's called being non-renormalizable.
Meaning you can't get rid of the infinities. With the other forces, we can sort of sweep them under the rug mathematically, right? Renormalization.
Exactly. We have techniques, renormalization, to tame those infinities for electromagnetism and the nuclear forces, letting us make incredibly precise predictions. Gravity just resists stubbornly.
So the math breaks down, spitting out nonsense infinities. Okay, what else?
Then there's the problem of time. It's quite deep. Quantum mechanics describes things evolving through time.
Like a movie playing out frame by frame.
Sort of. But in GR, time is part of the space-time fabric that is gravity. The core equations of GR don't really have a special external time parameter like quantum mechanics does.
So how do you describe evolution? Doesn't that lead to weird ideas like the universe being static or frozen at the quantum gravity level?
That's one of the deep conceptual issues, yes. And closely related is background dependence versus independence.
Okay.
Quantum field theory usually depends on having that fixed background space-time stage to define states and interactions.
The static stage we mentioned.
Right, but GR is background independent. Space-time isn't fixed. It responds to matter and energy. This is the gravitational field. How do you reconcile a theory needing a fixed stage with one where the stage itself is the main actor and constantly changing?
Yeah, that sounds like a fundamental philosophical divide almost, not just a calculation problem.
It really is. It's about the very nature of space and time. So, okay, Partonen and Tolkien. How do they propose to bridge this huge gap? What's their new angle?
Well, their core idea is pretty bold. They essentially sidestep the whole issue of quantizing curved spacetime directly.
Oh.
Instead, they propose that gravity is fundamentally a quantum gauge field, but operating within flat spacetime.
Flat spacetime. Hold on, like ignoring Einstein's curved spacetime, isn't that going backwards?
It sounds like it at first, but no, not quite like Newton. It's still relativistic, flat space, Minkowski space. But the key is the analogy they draw.
Analogy to what?
To the other forces in the Standard Model, electromagnetism, the weak and strong nuclear forces. They're all described as quantum gauge fields interacting in spacetime.
Right, mediated by particles like photons, W and Z bosons, gluons.
Exactly. So Partonen and Tolkien say, let's treat gravity the same way, not as geometry, but as mediated by, in their case, 4 interconnected quantum fields living in that flat background.
4 fields for gravity. Interesting. Not just the one graviton picture you sometimes hear about.
Apparently 4 interrelated ones in their setup. It's a gauge theory structure, similar in spirit to the Standard Model forces.
Okay, but then where does the curved space-time we know exists come from? General relativity works incredibly well. We see space-time curvature.
That's the really clever, maybe revolutionary part. They argue that the curved space-time of general relativity isn't the fundamental reality.
It isn't. Then what is it?
It emerges. It's the macroscopic average, the expectation value, technically, of their underlying quantum gravity fields operating in that flat background.
Whoa. Okay, let me see if I get this. The fundamental reality is quantum gravity fields in flat space. And the curved space-time we experience, the thing described by GR, is just what those fields look like on average at larger scales.
That's the core idea. It completely reverses the usual picture where mass curves space-time, and that causes gravity. Here, the quantum fields cause the appearance of curved space-time.
That is a radically different perspective. So the warp trampoline sheet isn't the real floor. It's more like an effect happening on the flat floor.
That's a good way to put it. And this ties into their symmetry-based approach. You mentioned they want standard model-like symmetries.
Yeah, what's the significance of that?
Well, the Standard Model is built on these beautiful mathematical symmetries, gauge symmetries. Partonen and Tolkien are trying to build their gravity theory using similar symmetry principles.
Hoping for unification, a shared language. Exactly. If gravity shares the same fundamental type of mathematical structure, maybe it's easier to link it up with the other forces. It's a focus on shared field properties rather than unique geometric properties.
Okay, that makes sense. Shifting the focus from geometry to field theory. So, does this flat space-time gauge field approach help with those nasty infinities? Renormalization.
Right. Back to the math. That's absolutely critical. If you can't renormalize, your quantum theory isn't really predictive. So what's the news here?
Well, they've reported a pretty significant success. They've shown that their theory can be renormalized for what are called first-order terms.
First order. Okay, so the simplest level of approximation in the calculations.
Basically, yes. Quantum calculations often involve series of approximations, getting more complex at each order. Showing you can cancel the infinities at that first level is a really important step. It means the theory isn't immediately dead in the water.
That is significant. It suggests the basic structure might be sound. But I sense a but coming. You mentioned first order. What about the rest?
Yeah, that's the crucial next step. And they acknowledge it's still an open question. They need a complete proof of consistency.
Meaning showing it works for all orders of calculation.
Yeah.
The higher order terms.
Exactly. They need to demonstrate that the renormalization procedure holds up as you include more complex interactions and loops in the calculations. They're optimistic, but the proof isn't there yet.
And if it doesn't hold up, if infinities reappear at higher orders,
then the theory, despite the promising start, might still be inconsistent. It could lead to predictions that blow up to infinity when you try to calculate things precisely, like having a solid foundation but finding the upper floors are unstable.
Okay, so that complete renormalization proof is the big hurdle they need to clear.
It seems to be the main one right now. But let's talk about an advantage they highlight. The theory's simplicity.
Simplicity in quantum gravity. That sounds refreshing.
Right. Compared to some other approaches, their theory is remarkably lean. It doesn't require any extra spatial dimensions.
Unlike string theory, which needs, 10 or 11 dimensions?
Well, exactly. And it also doesn't introduce any fundamentally new particles or forces beyond gravity and the known standard model stuff.
No supersymmetry, no exotic friends?
Nope. And crucially, no new free parameters, arbitrary numbers you have to measure and plug into the theory. It supposedly relies only on known constants like the speed of light and Planck's constant.
That sounds very appealing, actually. Why is that lack of extra baggage considered such a plus?
Well, fewer moving parts means it's potentially easier to test, right? If your theory predicts dozens of new particles or hidden dimensions.
You first have to find those before you can even test the core gravity part.
Precisely. Partonen and Tolke's theory, if it holds up, could potentially make predictions about quantum gravity effects that we might observe without needing to confirm a whole load of other exotic physics first. It's more direct.
More economical. Parsimonious, as physicists like to say.
That's the word. Okay, so assuming it is consistent, what kind of major problems could this approach potentially solve? What are the big payoffs?
Well, you mentioned the classic breakdowns, singularities, inside black holes and the Big Bang itself.
Where general relativity just gives infinite density, infinite curvature, basically throws up its hands and says, I don't know.
Exactly. A well-behaved quantum theory of gravity, like the one they're aiming for, shouldn't have those infinities. It should give a sensible description of what actually happens at the Planck scale in those incredibly extreme regimes.
So it could tell us what the center of a black hole really is, or describe the universe's very first moments.
That's the hope. To smooth out those singularities and provide a physically meaningful picture, that alone would be a monumental achievement.
Absolutely. And you hinted at something even bigger, the matter-antimatter asymmetry. How could quantum gravity possibly relate to that?
Yeah, that's one of the universe's biggest mysteries. Why is there so much matter and hardly any antimatter when the Big Bang should have made equal amounts?
Which should have just annihilated each other, leaving mostly energy.
Right. Parton and Tolke suggest, cautiously, that their framework, by potentially linking gravity deeply with the quantum field structure of the standard model, might open avenues to address this. It's speculative at this stage, of course.
But it hints at a possible connection between the force shaping the cosmos and the very nature of the particles within it.
It does. But again, these are potential applications if the theory proves fully consistent and can be developed further. They're not making guarantees, but highlighting the possibilities.
Understood. Exciting possibilities, though. Okay, let's get some context. This isn't happening in a vacuum. How does this new idea stack up against the, let's say, incumbents? String theory and loop quantum gravity.
Good point. These have been the leading contenders for decades. Let's start with string theory.
Okay, strings. What's the gist?
The core idea of string theory is that fundamental particles aren't points, but tiny, vibrating one-dimensional strings.
Like little rubber bands.
Kind of. And different ways they vibrate correspond to different particles, electrons, quarks, photons. And, crucially, one vibration mode matches the expected properties of the graviton.
The hypothetical particle that mediates gravity, so gravity just naturally falls out of the theory?
That's one of his big selling points, yes.
Yeah.
It offers a potential framework for unifying all forces and particles naturally. But, as you alluded to earlier,
Get extra dimensions?
the extra dimensions. To be mathematically consistent, string theory typically needs 10 or 11 spacetime dimensions.
Which we obviously don't see. So where are they?
The idea is they're compactified, curled up incredibly tightly, far too small for us to ever perceive directly. Think of a garden hose. From far away it looks 1D, but up close it has a 2D surface.
Okay, so the extra dimensions are hidden. What are the other big challenges for string theory?
Well, the biggest is the lack of direct experimental evidence. The energy needed to see the strings themselves or the extra dimensions is just astronomical, way beyond any current or foreseeable experiment.
So it's hard to test.
Very hard. There's also the landscape problem. The theory seems to allow a huge number, maybe 10 to the 500 or more, of possible ways for those extra dimensions to be curled up, each leading to a different universe with different physical laws.
So which one is ours? How do you find the right one?
That's the problem. It makes it incredibly difficult to extract unique, falsifiable predictions for our universe. And there are ongoing debates about background independence and significant issues matching the observed value of dark energy, the cosmological constant.
Okay, so mathematically rich, potentially unifying, but facing major hurdles with testability and uniqueness. Got it. What about the other main player, loop quantum gravity, LQG?
LQG takes a very different philosophical approach. It doesn't start with particles or strings. It starts with Einstein's general relativity and tries to quantize spacetime itself.
Quantize spacetime, meaning spacetime isn't smooth and continuous at the smallest scales.
Exactly. LQG suggests that space itself is made of discrete chunks, or quanta of geometry. Think of space having an atomic structure. These quanta link up to form network-like structures called spin networks.
So fundamentally, space is granular, like a digital image made of pixels.
That's the picture, yes. A key feature is that it's inherently background independent. It doesn't assume a pre-existing stage. The quantum geometry is the stage, and it emerges from the theory.
That sounds closer in spirit to GR than string theory, maybe.
In terms of background independence, yes. It takes that principle very seriously.
But LQG has its own challenges too, right?
It does. A major one is recovering the smooth classical spacetime of GR at larger scales, the semi-classical limit. How does this granular quantum geometry look like the smooth continuum we perceive? That's not fully solved.
Like showing how the individual pixels blend into a smooth image?
Good analogy. There's also, again, the tricky problem of time in a background-independent theory. And fully incorporating matter fields, like electrons, consistently into the framework has proven difficult. Some versions predict extra, unwanted mirror image particles.
And like string theory, no direct experimental proof yet.
Correct. While there are some potential subtle observational signatures proposed, nothing definitive has been found. And its main focus is really on quantizing gravity, not necessarily unifying it with the other forces in the way string theory aims to.
Okay. So string theory tries to unify everything via strings and extra dimensions. LQG quantizes space-time itself. How does Partnin and Tolke's theory stand out against these two giants?
Well, the starting point is the most obvious difference. Gauge fields in flat space-time. That's distinct from strings vibrating in some background, and distinct from quantizing the geometry of space-time itself.
Right. No extra dimensions needed either, which is a big contrast to string theory.
A very big contrast. And the nature of space-time is different, too. In LQG, space is fundamentally discrete. In this new theory, the background is continuous flat space, but the observed curved space-time is an emergent average effect of quantum fields.
So fundamentally different views on what space is at the bottom level.
Exactly. And then there's that claim of simplicity and testability again.
Because it doesn't add new particles or dimensions that need finding first.
Right. If we could ever measure quantum gravity phenomena directly, this theory might provide a more straightforward framework compared to needing evidence for strings, supersymmetry, or the discrete nature of space at the Planck scale first. They aim for a mathematically well-defined quantum theory without that extra baggage.
Okay, it definitely carves out its own niche, but let's circle back to its own challenges. What are the big question marks hanging over Partnin and Tolke's work right now?
Well, number one, underlined, bold, flashing lights, is that complete renormalization proof for higher orders.
The consistency check. Making sure the math doesn't break down when you calculate things more precisely.
Absolutely. That is non-negotiable for a quantum field theory to be taken seriously as predictive. While the first-order success is great, the physics community needs to see that full proof. They acknowledge this openly. It's the immediate task.
And assuming they clear that hurdle, what else?
Well, the universal challenge for all quantum gravity theories. Experimental verification. Gravity is just so incredibly weak compared to other forces at accessible energy scales. Detecting specifically quantum gravitational effects is monumentally difficult.
So even if the theory is mathematically perfect, proving it observationally is another mountain to climb.
A huge one. Although, again, the relative simplicity might make it slightly more testable if any quantum gravity signatures are ever found, because it has fewer prerequisites.
Fewer hoops to jump through observationally, maybe?
Perhaps. And, the theory is still young. Applying it in detail to cosmology, to black hole interiors, figuring out all its implications. That takes time and a lot more theoretical development.
It sounds like they're inviting help with that, though, calling for collaboration.
They are, very clearly. Publishing it in a major journal like Reports on Progress in Physics is essentially putting it out there for the community to pick apart, test, verify, and build upon. That's how science progresses, especially on problems this tough.
So they're saying, here's our framework, come help us push it forward.
Exactly. They seem cautiously optimistic that the path forward is workable, that the remaining challenges can be met with more research, and they expect progress in the coming years.
Okay, so let's try to wrap this up. What's the main takeaway from this deep dive into Partnin and Tolke's theory? What should we really remember?
I think the key takeaway is that this represents a genuinely different path towards quantum gravity. Treating gravity as a quantum gauge field in flat space-time, with curvature emerging later. That's a fundamental shift in perspective.
Not just tweaking existing ideas, but a new starting point.
Right. and one that potentially avoids some long-standing roadblocks like non-renormalizability, at least at first order, and the need for extra dimensions or particles, offering a potentially simpler, more parsimonious route.
So hopefully, mission accomplished for today. You should now have a pretty good handle on what this new theory is about, why it's different, and where it fits in the grand quest for a unified theory. A fresh look at the architecture of reality.
And it really does make you think, doesn't it?
Yeah.
If space-time itself, something we perceive as the absolute bedrock stage for everything, if that could be an emergent property, just an average effect of something deeper.
Yeah. What else that seems fundamental might just be an illusion or an emergent pattern from a weirder reality underneath.
Exactly. What other fixed certainties might dissolve if we look closely enough? It's a fascinating thought to chew on.
Definitely food for thought. And we hope it sparks some questions for you, too. What parts of this puzzle intrigue you the most now? Where might you want to dig deeper? Thanks for joining us on this exploration into the frontiers of physics and the hunt for the ultimate theory.